Hello, so welcome back to the next session of the LIPES workshop. So the coming session now will be dedicated to the process chemistry at the heart of the LIPES project. And I'm now handing over to Shirley Rusley from Technical University Berlin in Germany. So Shirley, the floor is yours.
Hi, thank you, Jan. Let me share my screen first. Good. Good. So, thank you, Jan, for the kind introduction. My name is Shirley, and in this section, I will talk about the background of chemistry of the LIPES project, and what kind of system are we dealing with, and what kind of approaches that we take to get an optimized condition for the process. In general, the process is aiming to shift from chemical processes to a greener technology using enzymes. We are dealing here with an oleochemical process for splitting vegetable oils, or in specifically the triglycerides in different vegetable oils, castor oil, sunflower oil, rapeseed oil into free fatty acid. And this process is actually a commercial process. Our project partner Oleon is actually one of the market leaders in this area, and they will talk to you about the application of the free fatty acid in a later section. And in our project, we are also trying to push this fatty acid into biopolymers, which will be done also with from DSM, another project partner. The main goal of the project is to shift from chemical processes which uses harsh conditions with a higher temperature, 250 degrees Celsius, up to 300 degrees Celsius, and at elevated pressure up to 50 bars. With enzymes, we can do the exact same reaction, but with mild conditions of 30 to 40 degrees Celsius and at atmospheric pressure. So not only that we can save a lot of energy by doing this process, we can also preserve the quality of the product, because sometimes we are dealing with temperature-sensitive fatty acids, for example, in ricinoleic acid. Then we can preserve the quality of the product. And not only that, we can also reduce the waste production and reduce water consumption using this the enzymatic process. A full list of the comparison between chemical and enzymatic process will be discussed later on in a later section. In my case, in this case, the biggest disadvantage of the enzymatic process is the high catalysis cost. As we might know, producing enzyme is much more expensive than producing synthetic catalysis, which means that it cannot compete with the conventional processes. So in LIPES project, we are trying to develop a process that reduces the consumption of the enzymes. We want to keep the enzyme active longer so that we can produce more fatty acid with a certain amount of the catalyst. In order to do that, we also have to scale up the process from lab scale into a pre-industrial scale with a reactor of 4,000 liter, so that we can reach some kind of economic scale. And to do that, we are a consortium of 5 partners, and as I said before, Oleon is the leader for oleochemistry. DSM evaluates the free fatty acid for production of biopolymer, and we have STC Engineering that provides engineering support to build this unit operation and the reactors. And we also have a partner in Wales from Biocatalyst that produce a novel enzyme specific for our processes. Myself, I am from Technical University of Berlin, where we focus on optimizing the different unit operation itself. So a short introduction to our university. We are located in Berlin, of course, with 4 other universities. As academic institution, we are focused basically on teaching, but we also have an integrated research facilities in the university. We are divided to 7 different faculties. We are in process sciences, process engineering, and we are the chair of chemical and process engineering. In our chair, we focus on 3 separate but also integrated research fields. we have a lot of background in multi-phase processes, in liquid-liquid dispersion, in liquid-liquid separation and mixing, which is also supported by the fluid dynamics. The fluid dynamics area, we focus on looking at the flow field around an impeller and comparison between a CFD simulation and the experimental data. In the previous years, we also have experience in integrating membrane into continuous processes with different micellar system. But in the recent years, we are focusing more on the reactor technology. For example, we have a project that is looking at bioreactors, how to reduce the shearing in bioreactors for shear sensitive materials such as cell cultures. And also in our project, in the LIPES project, we are developing a multi-phase reactor for enzymatic splitting of triglyceride. So why do we need actually a multi-phase reactor? Because we are dealing with two different liquids. We have triglycerides, which is soluble in the vegetable oils, which has to react with water. So here we have oil and water, we have to mix it so that the lipase itself can be absorbed on the interface between oil and water and then can react with the two different substrates. Therefore, the reaction rate is dependent on how many surface area we have inside the reactor. The bigger the surface area, the smaller the drops. That means the reaction rate is going to be faster. In batch reactions, in laboratory scale, it works completely fine. But to implement it in industrial scale, of course, we have to reuse the enzyme. We cannot just throw away the enzyme for every batch. Therefore, we are developing a continuous process where the oil and water is mixed and then separated into the respective phases, and the product can be taken. The product fatty acid can be taken from the oil phase, and the enzyme can be reused for further batches, for further processes. How do you optimize this process? We take a look into different separate aspects of the process. The first one is the reaction kinetic, and the second one is the enzyme deactivation. The reaction kinetic is dependent on the surface area, as I explained before, and we create the surface area by stirring the water and oil. The higher the stirring rate, the smaller the drops, the bigger the surface area, and the reaction is faster. However, on the other hand, if we stir the emulsion too high, we also create higher shearing that can lead to enzyme deactivation, which means that we want to have a fast reaction so that we can process as much as oil possible within the enzyme lifetime, but we also want to prolong the enzyme lifetime so that it can be reused for a longer time. These are the two different aspects that I will cover in this section. I will cover first the optimization of reaction kinetic, and later on I will focus on keeping the enzyme active inside the process. So to understand the reaction kinetics, of course, we need some experimental data. So we have an emulsion reactor and we stick an endoscope inside the emulsion. This is basically a long tube with a camera on the top so that we can take pictures of the droplets inside the emulsion. And we have an algorithm, an in-house algorithm to detect the drops, and we can analyze the size of the droplets, and then we can calculate the surface area. And here are the results. We can see that the higher enzyme concentration, we actually produce smaller droplets, which is good because the surface area becomes larger. And furthermore, from the oil phase, we can get an HPLC analysis to separate between the product fatty acid and the substrate triglyceride, so that we can know how fast the reaction has been going and what is the final hydrolysis degree, what is the final yield. And from this information, we also developed a kinetic model based on an enzymatic model of ping pong BB, because we are dealing with two different substrates, triglyceride and water. And this is basic enzymatic kinetics that has been going on for a long time. But we especially add an adsorption term before the reaction term so that we can simulate the limitation of the surface area. By adding this adsorption term, we can limit that only enzymes that are on the interface can react further with the substrate. Okay, now. And as the result, we can actually predict a saturation point when is all the enzyme molecules on the interface. Here you can see there are two different regions at low surface area. The reaction rate is dependent on the surface area. Here we have more enzyme molecules than the surface area available, which means that some of the enzymes are staying in the aqueous phase, in the bulk phase, and it's not available for reaction anymore. If we keep increasing the steering rate, or we increase the surface area, we then achieve the maximum reaction rate where all of the enzyme molecules are attached on the interface, and therefore increasing the stirrer speed doesn't increase the reaction rate anymore. To operate the system, we want to be in this saturation point. So because it doesn't make sense to blindly increase the steering rate, because we don't increase the reaction rate anymore. But increasing the steering rate will also mean that we higher the chances that the enzyme get deactivated. And to predict the saturation point is quite tricky with experiments because it depends on how much enzyme is also available inside the reactor. Therefore, there comes the benefit of reaction modeling. These dotted lines is actually the representation of the modeling results. And we can see here that for different enzyme concentration, the saturation point is achieved in different droplet size distribution, in droplet sizes. We are quite happy with the kinetic modeling here. I present to you the comparison of the results from the simulation and the experimental results. And these are experiments for different surface area from different steering rate at different enzyme concentration. And you can see that the model is able to predict most of the reaction with this wide range of conditions. Oops. Yeah. So what we have achieved so far is we can predict the optimal reactor design also for a larger scale based on laboratory experiments. We extract the experimental data and we model the mechanism, the reaction mechanism, and we have estimated the kinetic constants to predict the optimum condition for the reactor. If you are interested, we have published the kinetic modeling in a paper which I will give the link in the end of the presentation. And here you can see that there is a saturation condition, an optimum condition for at different enzyme concentration, what kind of droplet size you should have inside the reactor, and if you have a certain drop size, what is the maximum enzyme concentration you should give in. We can also predict the inhibition of glycerol, and we can also predict the limitation of water. Moving on, the reaction condition can be only predicted for a batch condition, but our goal is actually to have a continuous process, which means that we have to take care that the enzyme deactivation in such process is not too much, that we can reuse the enzyme for a long time period, especially when we have to scale up from 1 liter to 4 cubic meter of reactor. We are dealing with a lot of shearing in a larger order of magnitude. So what we do is we simplify the system. We take an enzyme from our project partner Biocatalyst. The enzyme is the lipomer34P, and we test this enzyme for different unit operations. We've tested in shearing inside the reactor. So basically just dilute the enzyme in water and then shear it for a longer time period. We also introduce aeration. We introduce gas bubbles inside the liquid to see the effect of interfacial tension. And we also observe the enzyme activity inside our emulsion where the reaction happens. For running a continuous process, we also need pumps. So we observe the activation in the pumps and also in the membrane where we have to retain the enzyme for the process. Here you can see that if we change the temperature, lipomode 34P should be stable at 30 to 60 degrees Celsius. And we make experiments up to 400 hours. And at different time step, we test the enzyme activity again and compare it to the initial enzyme activity. So here what you see in the y-axis is the residual activity at a certain time period inside the reactor. If you see here between 30 and 40 degrees Celsius, we really see no deactivation at all in shearing. But if we increase to 50 to 60 degrees Celsius, we see significant deactivation of the enzymes after 24 hours. Furthermore, we try to do the experiments for longer term shearing because we want to use the enzyme for more than 100 hours, of course. And you can see here that if we increase the power input, we see a big deactivation. This is mainly because we have a dead zone inside the reactor where the enzymes become agglomerated, and then we have a reduced concentration inside the reactor. This means that we need to actually have a proper mixing inside the reactor so that we have a constant enzyme concentration and not agglomeration of such reactor or such enzymes. Therefore, we tested different impellers. We tested Russian turbines and we tested a pitch blade turbine, which we called VHFI. And we steer it at 30 degrees Celsius and 40 degrees Celsius for a long time. And we don't really see any deactivation even though we increase the power input to 400 watt per cubic meter. However, if we increase it to 600 watt per cubic meter at 40 degrees Celsius, we see that after 400 hours, we start to lose some activity here, which indicates that there is actually a maximum shear rate. There is a threshold where the enzyme starts to deactivate. This phenomena is actually different if you have interfacial tension interface inside the reactor. So what we do is we put the stirrer higher up, so it's closer to the surface of the liquid, and then we start increasing the power input. At lower power input, we don't see any deactivation, but once we increase the power input, we see that it starts to build some vortices and it starts to suck in some air from the surface. We call it surface aeration. And due to these vortices, we see a lot of enzyme deactivation starting from the first 6 hours. This is something that has to be avoided at all costs in a stirred tank reactor. We can do it by adding baffles, or we can add cover on the liquid surface so that we can reduce the surface aeration. Another aeration that is common in bioreactors is aeration through sparger, when gas bubbles can be introduced through a tube. So we tested this as well, and we tried it with lower power input, and we don't see any deactivation. But once we increase the power input, that the bubbles are breaking, we see some deactivation after longer time period. So it's not like previously when we don't see any deactivation even though we increase the power input. Here we really see some kind of deactivation. And it can be explained when looking at the scale, the order of magnitude of the size of the particles, because enzymes are actually small molecules. It's relatively large to different to chemical substances, but it's ranging. The biggest size of an enzyme molecule is around 10 to the power of 9 meters, so in nanometer area. If we take a look at the eddies, turbulent eddies inside of a stirred tank reactor, we are talking in micrometer area. That means that the enzymes are actually much smaller than the streamlines, and that the molecules should be able to be transported within the fluid flow without being sheared. However, when we have a drop or a bubble inside the reactor, they ranges also in micrometer area, between 50 to 200 micrometer. And therefore that these droplets or bubbles are subjected to the streamlines, to the flow on the interface. And as we know before, that the enzymes are attached to the interface, and there they become trapped, they become rigid, and therefore is exposed to high shearing from the eddies, from the turbulent eddies. And that's when we see this kind of deactivation of the enzymes. Similar phenomena we also see in a water-oil emulsion when we have interface between oil and water. We also increase the power input, and this is a bit disconcerting because we see that the enzyme is deactivated with the activity is reduced within the 6 hours of reaction. But here you can see again and again we observe that the reactivation of the enzyme is possible. If we wait until the reaction is finished and then we test the enzyme activity again, we see that the activity becomes higher after 96 hours. And this indicates that that it's not a true deactivation. It's just because that the enzymes are absorbed on the interface and there are no more in the bulk phase where we test the enzyme activity. That could be the reason why it comes back more active after the reaction is completed, that the enzymes move back from the interface and back to the bulk phase. But of course, you can see here that between 300 and 600 watt per cubic meter, there are rarely reactivation of the enzymes, which leads us to believe there is actually really a maximum threshold or shear rate that a specific enzyme molecule can withstand. The same phenomena is also observed in membrane surfaces. We are talking right now then a solid-liquid interface where the membrane has is the solid and the aqueous phase is the liquid phase. And here we tested two different membranes, a dead-end filtration and a cross-flow filtration. Of course, if we have a dead-end filtration, most of the enzyme is stuck on the solid, on the membrane surface, and therefore we lose most of the activity after 20 hours. However, if we use a cross-flow filtration, some of the enzyme might get stuck on the, might be absorbed on the solid interface, but then the rest of the enzyme will continue with the flow and go back to the reactor. And this is what we see here, that the activity reduced up to 40% in the first 24 hours, but then it stays stable for longer term. This indicates that the membrane surface is fully covered by the enzyme molecules, and the rest of enzyme molecules that are transported to the membrane are now transported back to the reactor. In this unit operation, we tested the different enzyme concentration and the flux of the membrane, and you can see here that even though we increase the flux of the membrane, which means that we increase the pressure on the feed side, we don't see much more deactivation of the enzyme. But if we increase the enzyme concentration to 2 grams per liter, so double the enzyme concentration, we see that the deactivation is reduced. This indicates that with 2 grams per liter, we have enough enzyme to cover the whole area of the membrane, and therefore we don't see any deactivation inside the reactor anymore. So if a membrane should be used to retain enzymes inside the reactor, it is possible. However, initially we have to cover the solid surface of the membrane first with some enzyme concentration, and afterwards we can reach a steady state where we have a certain activity inside the reactor. However, when operating such membrane, of course, we need also to use some pumps. We tested different pumps, from peristaltic pumps to gear pumps, because they have different shearing inside the mechanism, and this is also pretty disconcerting that the enzymes are mostly deactivated in the pumps instead of in the reactor or in the membrane. So if we are looking at pumps, it's better to have 2 or 3 different parallel pumps working in a lower flow rate, so that we can reduce the shearing rather than having one big pump and with higher flow rate. So as a conclusion, if an enzyme has to be considered for continuous processes, this can be done because shearing alone does not really produce the activation in the enzyme, at least for the lipomotor D4P that we are testing. And it's mostly because the deactivation is happening mostly if we have interfaces in the unit operation. So if we have air liquid or cavitation in the pump, or this vortices inside the stir tank reactor, or even liquid-liquid interface like we have for our reaction, this can deactivate the enzymes because then the enzyme is subjected to higher shear rate. However, if the interfaces cannot be avoided, like for example our system with the emulsion, then we should investigate what is the maximum shearing threshold for this specific enzyme, that the enzyme doesn't completely denaturate it inside the reactor. That's actually all from my side. I will return it back to Jan. Thank you very much for your attention. And I hope it gives some kind of indication on how to optimize a process specifically for enzymatic reactions.
Well, thank you, Shirley. Indeed, this was a very interesting and nicely illustrated speech on the process chemistry at the heart of the LIPES project. I've got a couple of questions for you.
Yes.
The first one is why wouldn't we be able to use an immobilized enzyme to increase the stability or to reduce the deactivation of the enzyme?
Yeah, we have actually considered it in the project as well. And there are 2 arguments against immobilizing the enzyme. We use really free enzyme that is dissolved in the aqueous phase. The first one is because of the cost. Immobilized enzyme are always more expensive than the free enzyme, and we really need to reduce the enzyme cost as low as possible to be able to compete with conventional processes. And the more important reason is the mass transfer, because we are dealing with interfaces. We are dealing with 2 oil and water interface. With immobilized enzyme, the mass transfer from the oil phase, which has more viscosity, which has higher viscosity, is lower because if you immobilize an enzyme on a structure, the enzymes are usually hidden inside the porous structure, and the oil has to absorb, has to go into these pores. And if we are talking about high viscosity of oil, it's most likely that the mass transfer is hindered, that the substrate in the oil phase cannot reach the pores inside the immobilized enzyme. And that's why we are going with the free enzyme instead.
Okay. The next question is there a way to determine the maximum shear rate for the enzyme deactivation?
This is actually a trickier part to answer, because in a stir tank reactor, we need shearing to create the interface, but the shearing also causes the activation of the enzyme. So the 2 are not separable in a stir tank reactor. We have been developing a new setup, a new analysis setup, where we can apply a certain shear rate on interface between oil and water. So we have a rheometer where we can create an interface between oil and water, and then we applied as controlled steering. And we are really hoping that we can determine the maximum shearing on the interface, that we see a denaturation of the protein molecules itself.
Okay, well, thanks again, Shirley, and thank you all for watching this speech. Don't hesitate to leave us a comment. our question, and we'll try to answer it on the website. Thank you.
Thank you.